Welcome to lecture 5.3, discontinuous forcing terms. Okay, so the first thing I want to do is I want to define three very basic discontinuous functions, and we will use these as building blocks to express and write more complicated discontinuous functions later. But for now, I just want to show you what these things look like. This is like bracket notation or case-by-case notation. This is usually how we express discontinuous functions, at least in high school. And later in this lecture, I will show you a better way using these functions as building blocks. But for now, let's plot these things. This first one, it's 0 outside of the interval AB, and it's 1 on the interval AB. So it looks like this. The second one, the Heaviside function, this is a function that's going to be it's going to be 0 left of the y-axis, so for all negative numbers and for 0, and it's going to be 1 for all positive numbers. And then the shifted Heaviside function, this thing is, if this is C, then the shifted Heaviside function is 0 up to here, and then it's 1 after C. So let me say a couple things. So the shifted Heaviside function, of course, can be written as the Heaviside function of t minus c. The Heaviside function, in the spirit of the interval function, some people will write this. I don't usually do this, but you can think of it as the Heaviside function from 0, or it's the interval function from 0 to infinity. So it's like the interval function where it never really closes up. So let's write that. And similarly, you can write this, if you want to, as hc infinity of t. And then the last thing, or I guess there's two more things I want to say. First of all, I'm using the convention that when I have something like this, I make this less than or equal to, and the right-hand side one a less than is a strict less than. It really doesn't matter for these type of functions because we're going to be computing Laplace transforms, which is integrals, which is area under the curve, and it doesn't really matter whether this endpoint, whether we include it 0, or then we include it down here where it's 0, or make it 1 up here. So I just like to be consistent, and I usually write these things like this. But I'm sure you'll probably find some textbooks where maybe this convention is switched. And in certain areas of mathematics, it actually does make a big difference. If you study Still's integration, which is a senior level math course in real analysis, it does make a difference whether these are less than or equal to's. But for this class, it does not. The second thing is that technically there aren't any vertical lines here, but often it's just easier to write these things with the vertical lines. So sometimes we'll draw these things like this, and the vertical lines really don't exist, but it's convention to draw it. So if you see them, that's what they're there for. Okay, and then the last thing so there's actually one more thing I want to say. The interval function, which is HAB of t. Oh, let me make that a little better. Make the t bigger. HAB of t. This thing, I claim I can actually write this as the difference of two Heaviside functions. So I claim this is HA of t minus two shifted Heaviside functions, B of t. And let's see why that is. So if I have an interval, let's actually do this one up here. If I have this interval function, then I can write that actually as the Heaviside function, or I should say that the shifted Heaviside function. Oops, let me draw that better. So this is the shifted Heaviside function. This is HA of t, where this is A, and then I want to subtract off the shifted Heaviside function HB of t. And notice what I get if I take this blue function and this function here, and I subtract off this function, that everything to the right, this is, of course is b, everything to the right of b is going to be 0 because this cancels with this. Everything to the left is 0, and I get the interval function. So the interval function can be written as a sum of shifted Heaviside functions, and then I always like to write h of t. So what we'll do is we'll write this, we'll write these things as h of t minus a minus h of t minus b. So we're going to end up writing all of these things and then other piecewise functions using only shifted Heaviside functions. So something like this. Okay, so let's do some examples. This first function up here, well, let's sketch it first. So that's going to be between 0 and 1, it's going to be this function, 2t, and then from 1 onward, it's going to be a constant function 2. So let's just write this using the Heaviside function. So this first part is the interval function. So f of t equals it's 2t times the interval function on 0, 1. And then the second part is just the constant function 2 times the shifted Heaviside function 1 to infinity. So 2 times the shifted Heaviside function t minus 1. So let's write this out now, as we did before, as a difference of Heaviside functions. So this is h of t minus, oh sorry, this is 2t, h of t minus h of t minus 1, plus 2 times h of t minus 1. So if we collect terms, I think we can write this. Let's write the h of t terms first. That's 2t times h of t. And then everything else, we have a 2 and a minus 2t, so I can write that as 2 times t minus 1 times h of t minus 1. So there is this piecewise function written using the Heaviside function. And again, we do this because we'll see very soon how to compute the Laplace transform of this quite easily. Okay, so the next function is, let's get my pen back. So this is the function that is 3 on 0 to 4. Then it's negative 5 from 4 to 6. And then it's I don't know, this is an exponential function. I'm not quite sure how high it is, but it's going to be something like this. I don't know if this thing starts up here or down here. Something like this. Actually, I think it should start at, it should start at e to the 2.71, so slightly below 3. And yeah, it looks like this. And if you want to, you can put in the vertical lines or just dashes. So let's do the same thing we did above. Let's break this into 3 pieces. So this first piece is the function 3 times the interval function from 0 to 4. So this is 3 times the Heaviside times the interval function 0 to 4. And then the second one, this is function negative 5, so I'm going to write that as minus 5 times the interval function from 4 to 6. Interval function from 4 to 6. And then this last piece here is e to the 7 minus t, so plus e to the 7 minus t times the shifted Heaviside function, that's h of t minus 6. So now let's simplify this using, let's write this only in terms of Heaviside functions. So this is h of t minus h of t minus 4. This next term is minus 5 times h of t minus 4 minus h of t minus 6. And then this last term is, well, keep it the same way, it's e to the 7 minus t times h of t minus 6. And now let's collect terms. We have 3 h of t's here. How many h of t minus 4's do we have? We have negative 3 and we have negative 5. So that's minus 8 times h of t minus 4. And how many h of t minus 6's do we have? We have positive 5 of those. So we have plus h of t minus 6. And then we have this last term. If I wanted to, I could have combined these two terms into one, but I'll keep it separate for now. H of t minus 6. And that is our final answer. That is this function here, written as a sum of Heaviside functions. So here is the key piece of information that helps us take the Laplace transform of a piecewise function. So let's talk about what this says. Suppose you have suppose you know the Laplace transform of a function f of t, then the Laplace transform of this creature is the same function, capital F of s, times an exponential. So let's draw a picture of this so we can understand what this is all about, because without a picture it's hard to make sense of this. So how to interpret this? Let's suppose we have a function. So here's a function, say this is f of t. Now, I'm sure you know that if you want to shift this function by c, then that function is just f of t minus c. It's just basic high school algebra. Okay, so now let's compare, let's look at this function, f of t times h of t. If we multiply this function by a Heaviside function, what that does is that chops it off left of the origin. And now why am I doing this? Notice that Laplace transform of f of t, this is the integral from 0 to infinity of f of t times e to the minus st dt. Now that's the same thing as, you can't stop me from writing f of t h of t e to the minus st dt. Multiplying by the Heaviside function, that's just multiplying by 1, or at least for t greater than 0. And since we're integrating from 0 to infinity, it doesn't matter what I'm doing left of the origin. So what this does is this chops off our function left of the y-axis, but that doesn't matter because we're integrating from 0 to infinity. So notice that this thing here is just the Laplace transform of f of t, h of t. In other words, what we're really doing when we're computing the Laplace transform of a function is we're computing the Laplace transform of the function times the Heaviside function. So now what we want to do is we want to compute, so this property talks about the Laplace transform not of our function but of this thing. And what is this thing? That is the shifted version of this thing. So now if we want to actually shift our function, say this is f of t minus c, h of t minus c, if we want to shift this function by c, what we don't want to do is we don't want to introduce a piece of the function which did not come into play before when we computed the Laplace transform. This thing left of the y-axis could have been anything. So the natural thing to do is to compare the Laplace transform of this function to the Laplace transform of this function, not of this and not of this. And so what this is saying is that the Laplace transform of these two functions differ. So the Laplace transform of this function, if this is just if this is f of s, then the Laplace transform of this function is just compute L, and that goes to f of s times e to the minus s. So the only difference in the Laplace transform of a shift is an exponential. Oh, I forgot my c. E times, put a c right there. So one way to say that, what engineers will say, is that a shift in the time domain, corresponds to multiplication by an exponential in the frequency domain, in the s domain. Now let me remind you of another thing that we saw, I think in the last lecture. So this is, so let's call this a remark. This is in some sense dual to the following property that we saw previously. The Laplace transform of e to the ct times f of t is f of s minus c. Remember that? So let's talk about in words what this says. This one says that multiplying by an exponential in the t domain corresponds to a shift in the s domain. Whereas this one says multiplication by, an exponential in the s domain corresponds to a shift in the t domain. So in either one of these, we say that multiplication in one domain, t or s, time or frequency, corresponds to, I should say multiplication by an exponential corresponds to a shift in the other domain. Okay, so let's finish with an example. So let's compute. Let's do this. Let's put a line here. Let's use this to compute the Laplace transform of a function that we've seen before. So let's compute. Let's say f of t is our function 2t from 0 to 1, and it's 2 from t greater than or equal to 1. So it's this function. Remember that one? Or this is 1 and that's 2. And now recall that we actually a couple slides ago we wrote this function as 2t h of t minus 2 t minus 1 h of t minus 1. So let's compute the Laplace transform of this. So the Laplace transform, capital F of s, this is the Laplace transform of, well actually let me pull out the 2. So this is the 2 times the Laplace transform of t h of t minus 2 times the Laplace transform of t minus 1 h of t minus 1. And now remember that the Laplace transform, let me put it, the Laplace transform of t is 1 over s squared. Remember that? So this term here, that's just the Laplace transform of t. Because remember, we can always multiply by h of t and not do anything. So this is 1 over s squared. And now what is this? This thing here, that's perfect for using this formula. This is a shift of this function by 1. So the Laplace transform of this is 1 over s squared. We have to multiply by the exponential e to the negative cs. So times e, oh, let's get my pen back, e to the negative cs. So this thing here is just, let's not forget our 2. So that is, this is 2 over s squared minus 2 over s squared times e to the minus s. And so that is the Laplace transform of this thing. And we're going to use this because later in this lecture we are going to solve a differential equation where the forcing term is this function. So we'll revisit this function shortly. Let's do some examples of this just for practice. As we'll see, some of these you can do in your head and others are a little more complicated, but I'll show you a neat little trick that's always going to work. Okay, so the first one, compute the Laplace transform of this. The first thing you should do is you look at the 3 and you say, well, that has to be c, just based on this formula. That's what c is. So therefore, this function here, that is f of t minus c equals t minus 3 squared, that's f of t minus, let's say, 3. Let's write it like that. F of t minus 3 is t minus 3 squared. Okay, so now maybe you can just look at this and say, well, that must mean that f of t, so if f of this thing equals this thing squared, then f of t must be equal to t squared. And that means that the Laplace transform of that is 2 over s cubed. Remember that? Okay, so our Laplace transform, our final answer, is e to the minus 3, not 3c, 3s, sorry, 3s times f of s, which is e to the minus 3s times 2 over s cubed. So there is our final answer. Let's make sure that's a dot and not a subtraction sign. Okay, so let's do our next example. Our next example, you look at the 3 again, and you say, well, c has to be 3. And then you look at this, and you say, well, f of t minus 3 equals t squared. So that means that f of t equals, well, how do we do this? It's not quite so clear what f of t is if f of t minus 3 is t squared. Now you might be able to see it in this case, maybe, maybe not, but let me show you a surefire way that's going to work. So what I like to do is, I look at that t and I want to plug in, let's plug in, and for t, what if I plug in t plus 3? Then this 3 is going to cancel with that 3, and we get f of t. So if we replace every instance of our variable t with t plus 3, let's do that. So f of t equals f of t plus 3 minus 3. So that's certainly f of t, right? And now let's plug in t plus 3 in for here. So if I do that, I get t plus 3 squared. And that's f of t. Now maybe you did this in your head before I got here, but there's going to be ones where you won't be able to do this in your head, and this will be a neat trick. So the Laplace transform of this, how do we do that? Well, we first need to multiply this out. Make it t squared plus 6t plus 9. So the Laplace transform is, well, it's 2 over s cubed plus 6 times 1 over s squared plus 9 times 1 over s. So the Laplace transform of this thing is just e to the minus 3s times f of s, which is e to the minus 3s times this creature, which is 2 over s cubed plus 6 over s squared plus 9 over s. And that is our final answer. Okay, so let's do another one. Laplace transform of f of, f of t minus 1. I'm going to do one a little different. I'm going to change this to not t minus 1 squared, but let's make this e to the t minus 1. So let's compute the Laplace transform of e to the t minus 1 times h of t minus 1 to make it a little different. Okay, so if we do that, then again, you look at this and you say, well, c has to be equal to 1. And you can look at this and you can say f of t minus 1 has to be e to the t minus 1. So you could probably just by inspection look at that and say f of t is e to the t. But let's do our little trick. Let's plug in t plus 1 in for our t's. So plug in t plus 1 into our t's. And then we get, so we get f of t equals f of t plus 1 minus 1. So take our e to the t minus 1 and plug in t plus 1 minus 1, and we get e to the t. So the Laplace transform of this is 1 over s minus 1. So our Laplace transform of this original thing is e to the minus s times f of s, which is e to the minus s over s minus 1. There we go. And finally, let's do another example down here. Actually, this is not the example that I had. I'm gonna change this one as well. I want to make it match the problem that we did before. Let's compute the Laplace transform of e to the, remember this one, e to the 7 minus t times h to the t minus 6. Let's do that. So this one, even if you could do the second one in your head, you probably cannot do this one in your head. So here we look at this, we say c equals 6, and therefore this thing better be, that is f of t minus 6 equals e. So I'm going to write e to the, I'm going to write this as, oh no, I'll leave it like this, e to the 7 minus t. I was going to factor out the e to the 7, but okay, so let's make a line here. So this means that f of t plus 6 minus 6, so we're going to plug in t plus 6 in for there. So that's going to be e to the 7 minus t plus 6, which is e to the 1 minus t. Now I'm going to write this as e to the 1 times e to the minus t. Okay, so this e to the 1, this is just a constant. So think of it as just a number. So the Laplace transform of this is that constant times the Laplace transform of e to the minus t, which is 1 over s plus 1. So our Laplace transform here is going to be e to the minus 6 times s times Laplace transform of this guy. And so that is e to the minus 6s times e to the first times 1 over s plus 1. Let me move this thing down here and simplify that a little bit. So I can write this is e to the 1 minus 6s times 1 over s plus 1. And that is our final answer. Okay, so let's now compute the Laplace transform of this piecewise function that we saw a couple slides ago. Remember that this is the function that, let me actually not draw it like that. Let's draw it more like this because it was 3 and negative 5. So between 0 and 4 it was the function 3. Between 4 and 6 is the function negative 5. And then between 6 onward it was this exponential function, which started at e and went down to 0. So this is f of t. And recall a couple slides ago that we actually computed the Laplace transform of this function. No, we didn't compute. Sorry, we wrote the function using the Heaviside function, and this is what we got. So let's now compute the Laplace transform of this function. So let's do it term by term. So this first term, well, let's write f of s. So this first term is the Laplace transform of 3. So that is, the Laplace transform of 3 is just 3 over s. And recall, h of t, we're just multiplying by 1. That doesn't actually do anything when we're computing the Laplace transform. Now this next one, so this is going to be minus 8 times, well, let's compute the Laplace transform of this. Well, this is actually in the form as this thing up here, if f of t minus 4 equals 1. So recall that the Laplace transform of 1 is 1 over s, so we can apply this formula here to this term, and we get e to the minus s, sorry, e to the minus 4s. Let's write that a little better, because again, c is equal to 4, so it's e to the minus 4s times the Laplace transform of 1, which is 1 over s. Now, same thing here. This is just, oh, that's not what I meant to write. That's this over here. We can also apply this formula where f of t minus 6 is equal to 1. So this is plus 5 of e to the minus 6s times 1 over s. And then this last term, this is what we did on the previous slide. And if I remember right, I think it is e to the 1 minus 6s over s plus 1. So if you want to, you don't have to, but you can collect terms and write this as 3 minus 8 e to the minus 4s plus 5 e to the minus 6s all over s, and then add this to e to the 1 minus 6s over s plus 1. Okay, so I want to finish the lecture with an example of a problem that I've talked about is very important and one of the main reasons for studying Laplace transforms in the setting of ODEs. It's solving a differential equation when our forcing term is piecewise, something where we can't, it's either piecewise continuous or it's piecewise differentiable. So in this case, our function looks like this. It's got a little corner. This is 1, this is 2. And so our calculus methods, such as using the method of undetermined coefficients, is out, goes out the window. Okay, so one thing to, I guess before we get started, let's recall that we've actually written this function using the Heaviside function before. So this, we did that, f of t. This was a couple slides ago. I think what was it? It was 2t times h of t minus 2t minus 1 h of t minus 1. And we also computed the Laplace transform of this. That was f of s. That was a couple slides later. It was 2 over s squared minus 2 over s squared times e to the minus s. Okay, so now the first thing to do is to compute the Laplace transform of both sides of this equation. So let's apply L to both sides, and we get the Laplace transform of y double prime plus the Laplace transform of y equals the Laplace transform of the forcing term. Let's write that a little better. Okay, so the Laplace transform of y double prime is s squared y minus s y of 0 minus y prime of 0 and then the Laplace transform of y is just big Y, and then the right hand side is 2 over s squared minus 2 over s squared times e to the minus s. So remember that this initial condition is 0, so that's going to kill off this term, and this is 1, so that's going to be 1 right there. So if we simplify this, we get s squared y minus 1 plus big Y equals, and now let's combine this into a single fraction because we're going to want to solve for y here. So this is going to be 2 minus 2e to the minus s over s squared. Okay, so let's factor out a y in these two terms and move the 1 over to here. Okay. Is that what we should do? Sure. Yeah, let's do that. So let's do s squared plus 1 times y equals 2 minus 2e to the minus s over s squared plus 1. So now we can solve for y, and we get that y equals, so y of s is, so divide through by s squared plus 1 under both of these terms, and we get 2 minus 2 e to the minus s divided by s squared times s squared plus 1. And then the other term is plus 1 over s squared plus 1. So here is, let's circle this right here because this is, remember our first milestone is to solve for y. So once we have y, now we need to, all we have to do to solve this is we have to compute the inverse Laplace transform of this creature. So to do that, we got two terms separately. This thing, that's not going to be that bad, but we need to use partial fractions to break this up. And did a little bit of so I came prepared. Partial fractions. So if we have 1 over s squared times s squared plus 1, then that is just 1 over s squared minus 1 over s squared plus, wait, is that? Yeah, that is right. So that's 1 over s squared plus 1. This is something you can plug this directly into Wolfram Alpha, or you can do it by hand. Okay, so back to here. We want to split this up into, so let's split this thing up into two fractions, 2 over this minus this thing over that. So I'm going to write this as, let's see. So I want to do it in, so I'm going to write this as 2 over s squared minus 2 over s squared plus 1. That is just this fraction here applied to this. And then we also have, a term, so we got to do this term here. That's minus 2 e to the minus s over s squared minus 2e to the minus s over s squared plus 1. And then this last term right here is 1 over s squared plus 1. So again, these two terms come from 2 over this fraction broken up according to this, and then these two terms come from this fraction broken up according to this. And I think we can simplify this a little bit. So let's see. We have 2 over s squared plus 1, and here we have 1 over s squared plus 1, or minus 2. So these things can combine. So let's write this as use blue now, 2 over s squared. Then we have minus 1 over s squared plus 1, right? And then we have, let's do these terms. So those are straightforward. So then we have minus 2e to the minus s over s squared. And then we have plus 2e to the minus s over s squared plus 1. Okay? So now this is y of s. So I can actually box this because this is more important than the previous thing that I boxed. This is it broken up into terms that we can handle. So now the inverse Laplace transform of this, let's just do it piece by piece. So this is it's 2 times the inverse Laplace transform of 1 over s squared minus, I'm going to actually move this term first. I'm going to put the s squared terms together. So that's going to be 2 times the inverse Laplace transform of e to the minus s over s squared. And then we're going to have minus the inverse Laplace transform of 1 over s squared plus 1 plus 2 times inverse Laplace transform of e to the minus s over s squared plus 1. So this is the solution to the initial value problem up here. We just have to compute each one of these Laplace transforms separately. And to do this, let's remind ourselves of that very useful formula that we learned a couple slides ago, that the Laplace transform of f of t minus c, it's not f of t minus c, f of t minus c times h of t minus c, that is e to the minus c times s times f, that's a c, that's an f, times f of s. So we're going to use that down here. Okay, so the first one, the inverse Laplace transform of this is, let's see, this is 2 times, this is just t, right? Now this next one, this is, so here we want to use this formula. Let's go backwards, starting from here. So f of s is 1 over s squared. So the inverse Laplace of that is going to be t. So negative 2t, so let's write negative 2t, but we have to shift by 1. So c here is 1. So instead of t, I need to write t minus 1 times h of t minus 1. Now this next one, this is just straight out of the textbook. This is sine of t. And then this last one, this is plus 2. Now again, this thing calls for this formula up here, so the Laplace transform f of s is going to be 1 over, it's going to be this function here. So it's going to be sine of t, but again, we don't want to just leave it as t, because we're shifting because of this thing. So we have to say t minus 1 h of t minus 1. So now let me collect terms. Here I'm going to collect all the terms together that don't have any Heaviside function and ones that do. So I'm going to write this as, so first of all we have 2t minus sine of t, and then I'm going to write that as, I don't have to, but I'm going to multiply that by h of t, just because that doesn't do anything. That's the same thing as 1. And then what's left, we have plus, let's see what else we have left. So now we have this term and this term. So that's, I'm going to write as this minus that. So 2 sine of t minus 1 minus 2 t minus 1. This whole thing is times h of t minus 1. So this is our final answer. This is our y of t. This is our solution to the initial value problem. But now I want to do one more thing. Since it's always nicer to write a piecewise function, in cases like this, bracket notation, I want to take this thing that we've written in Heaviside notation and write it like this. Because it's not clear at all what this thing looks like if we were to graph it. So we sort of want to do this process in reverse. We want to go from Heaviside notation to bracket notation. So I'm going to do that up here. I'm going to write y of t equals, I'm going to rewrite this function. Now, how do we do this? I'm not going to teach you anything new. We just got to take what we learned and do a little critical thinking. So there's going to be one breakpoint at t equals 1. So, or assuming that our domain is for positive t. So in other words, there's going to be something for t greater than or equal to 0, or maybe just greater than, actually that's not quite right. I should say there's something for t between 0 and 1. And then there should be something for t greater or equal to 1. And let's make sure that looks like a 1. Okay, so how do we do this? Now, here's the key. I'm circling the two Heaviside functions. These things are just numbers. And they're not just any number. They're very simple numbers. They're either 1 or 0. This thing here is going to be 1 in both of these regions, from 0 to 1 and greater than 1. And this thing here is going to be 0 in this region and 1 down here. So up here, this thing is 0, so let's ignore this entire term. Get rid of it. And let's make this thing equal to 1. So when we do that, all we get is this thing here times 1. So let's write that down. So 2t minus sine of t goes up here. Now what goes down here? Let's set both of these things equal to 1. This is 1 and this is 1. Then they go away and we just have to add this thing plus that thing. So let's actually check up here what that is, because I think we can simplify something. So let's see. So if 2t minus sine of t, take that, and then let's add this thing to it. We get 2 sine of t minus 1 minus 2t minus 1. Some things are going to cancel here. I think that 2t is going to cancel with that 2t, because we have a negative sign there. So this thing is going to, what are we going to get? So that's going to cancel with that. So we get 2 sine of t minus 1. Then we're going to have a, what else do we have here? We have a plus 2, or as, well, let's see. So we have a minus sign right there, and then we're going to have a 2, because there's a minus 2 times negative 1. So we have sine of t, and then plus 2. Okay, so let's move this whole thing down here. I'm going to write this as 2 plus 2 sine of t minus 1 minus sine of t. So this is our final answer, written in bracket notation. And it's not surprising that, because our forcing term is piecewise, we had some not discontinuity, we have a corner here, some undifferential behavior, then our solution should also be piecewise as well.